All right. Oh, that's why. Good morning, guys. I'm not hearing anything because I mute my speaker here. Okay. All right. So let's start today's lecture with the example that we sort of like did a little bit of the problems in electric fields last time. So what we are going to do today is we're going to use these examples as a review and just remind you what we did last time. Yeah, sounds like a good plan. All right. I hope you still remember how. And the good thing is, what we are going to do today is still in the business of electric field. And toward the end of today's lecture, you're going to have to face calculus as expected. All right, there's no sound effects today. Okay, so in the figure, you have four particles are fixed in place, and you have charges Q1, Q2, Q3, Q4, and each one are given the amounts of charge, like 5 times the electronic charge, 3 times, 12 times. Q1, Q2, and Q3 are positive charge, and Q4 is a negative charge. Okay, so the value of the distance D is given to be 5 microns, which is, we can do the numerical calculation toward the end. That shouldn't be a problem. So the question is, what is the magnitude of the net electric field at point P? That's where you want to figure out, okay? And of course, you have to calculate the electric fields from 4 charged particles over here. So that means eventually you're going to have to combine all 4 vectors together to find out what is the resultant electric field at point P. Okay, cool? Already. So first thing first, all right, just remind you, every charged particle will have electric field around it. So let's start from Q1, shall we? So just imagine that around the charge, you always have this electric field coming out because Q1 is positive charge. So the electric field diverges from it, okay? However, what we care about at this point is what is going on. Oh, I think I undo too much again. What we care at this time is just what happens at point P. So you just imagine this. There is a line coming out here, a faint one here. See that? All right. So electric field is supposed to get out everywhere, but only the direction that we care about is just the one that actually going through P. So at P, you will have an electric field due to Q1, and it's going to point away from it because Q1 is positive. You guys with me? Cool. All right, then. So we can calculate the magnitude of that. So let me name this E1. That's a vector due to charge Q1. Okay, and the magnitude of the charge of the field E1 is just going to be K. The charge that's generating the field, which is Q1 itself, and the distance from the charge to the point of calculation, which is D. So it's going to be over D squared. Cool. That's not bad. All right. And if you want, you can substitute the value into it, even though, well, I don't need to. K is just 9 times 10 to the negative 9. That's constant. Q1, you can put it like 5e. And once again, I want to emphasize here that in calculation of the magnitude, I don't need to put any sign of the charge anymore. Okay, you guys with me? Yeah, because we already figured out the direction of the electric field E1. So I think everything is good. So all you care about is just what is the magnitude of the charge, which is 5 times the electronic charge here over D squared. All right, I'll just leave it there. All right, we can substitute the numerical values toward the end. That should be fine. Let's move on to the charge due to Q2. Yeah, just try again. So once again, Q2 will generate electric field everywhere around this. Okay, just come out of it. All right, and because Q2 is positive, so the electric field will be diverging out from Q2. All right, but what we want is just the electric field at the location of P1. So once again, at P1, it will have electric field pointing out. You guys with me? So far so good. All right, so I'm going to name this electric field E2. Okay, I put a vector arrow on top. Okay, and I also can calculate the magnitude of this electric field is going to be K times the charge that's generating the field, Q2, over the distance. And the distance, once again, is D. So you just put D and then you square it. And now I can substitute the value a little bit. K is K. The magnitude of the Q2 is still 5E. The distance is D squared. So one thing that you notice right away, E1 and E2 are having the same magnitude of the electric field. Yes. So that means, all right, these two cancel. There's nothing left for you to calculate here. Is that cool? So this is a sort of like benefit of not putting the numbers into it right away. It seems to me like most of the time it works out pretty well by every time that you want to do the final numerical calculations, you do it at the last step. If there's something that you can use just like a parameters, some constant and stuff, you just leave it there, right? And then you just do complete analysis first, and then once at the end, you just substitute the numbers in, and then you do the final like calculator punching and everything just at the end, right? The last step. So that's kind of like, it's always, I don't know, it's good. Save sometimes, yeah, just like this one, yeah, you don't have to do anything, just they're already canceled. All right, now move on to Q3. So once again, Q3, of course, around the Q3 we'll have electric field everywhere, just like normal, right? So I'll try to write this like dirty electric field lines, just so annoying you, just to annoy you that these are fields that's already there. It exists around any charged particle. Okay, but for us, what we care about at this point is what is going on at point P. So because electric field is coming from Q3 charge, which is still positive. Okay, so electric field will just diverge out from it. So at P, you will get an electric field coming out. Cool. All right, everything so far so good. And once again, I can name this one E3 vector. And if I want to find the magnitude, I just take just E3. And I mean, just for clarity, sometimes you might see the notation for the magnitude to be this full form like this. They are the same. Okay, you can write the electric field vector with the arrowhead on top, and then you put the absolute sign just to signify that you want to calculate the magnitude. Or you just simply put E3 without any arrowhead. I think everyone will understand the same thing that you are mentioning about the magnitude of the electric field. So the value of this one is what? K, yeah, cool, times the charge, Q3, divided by the separation from the charge to the point of calculation, which is still D anyway. So you just put D squared there. All right, just do one more step of substitution. K, Q3 is 3 times the electronic charge over D squared. All right, just keep it there. Now the last one, guys, it's the Q4, right? And the Q4, once again, it will generate electric field everywhere, except now electric field from Q4 is going to be converging toward Q4 because Q4 is a negative charge. Okay, you guys with me? All right, so that means what you can get out of this is you're going to get an electric field pointing towards it. You guys with me? Yeah, pointing towards Q4. All right, I'm just write it there. There you go. So at point P, you will have an electric field pointing towards the Q4 that is originating the field. All right, how much? All right, what you can say. All right, let me do the color coded here. I'll do the orange one here, E4 vector. So the magnitude of the E4 is going to be K, Q4 over now the separation from Q4 to point P is now it's 2D. So it's going to be 2D, the whole thing squared. Substituting the value into it, I get 12E. See, I don't need to put the negative 12 anymore because this is the magnitude. Magnitude of a vector never go negative. All right, divided by 4D squared. And when you cancel this number, you get number 3 out on top. And look at that. Isn't that nice? They are exactly the same as the magnitude of E3. So the good thing about this one is, once again, it turns out E3 and E4 sharing the same size, except they are pointing in the opposite direction. So that means you get cancellation again. Cool. All right, we're supposed to have like a big sound effect now. All right, so at the end, the net electric field at point P, you can just say it's just zero. It's just perfectly canceled. All right, so you get zero electric field at point P, and then you are done. Cool. All right, guys. So I hope by doing this problem here, that's remind you what we did last time, that first of all, and second of all, you can see that sometimes you might have an arrangement of electric particles, charged particles that might not arrange in XY axis or anything. It's just sort of like freely distributed in space. All right. But the key is still the same. Electric field is pointing in the radial direction, having your charge that generating the field to be the center of everything. Cool. All right. So that's a question comes in. So it doesn't matter what amount of charge we put at P, it will stay still, right? Correct. Actually, yes. So that's a very good question. So it means if I place a charge here, okay, let's say the fifth charge, then it will feel nothing. There will be no force acting on it because the fields at that point is zero. So if you carefully place it there exactly, it's going to stay there. Yes, you're right. Yeah, but in reality, it's kind of tough to be able to be like, you know, super exact there. But yeah, in theory, that's what it is. Yep. So you can say force at point P is definitely going to go to zero as well because there's no field there. Yes. Cool. Already. All right. That's and it's kind of fun now. Okay. So what else can we do with this? So once we sort of like get to see a little bit of electric fields and the connections with the electric force, and the idea is so simple, right? Because I keep saying that just think of gravitational force and the gravitational field. Whenever you want to get your weight calculated, all you need to do is just take the mass times the gravitational acceleration, g. It's mg. You get your weight. Same thing over here. You want to get electric force. You take the charge, multiply it by the electric field. It's a QE. You get the force. Done. So what you have next is just now, in reality, you might have electric field that go crazy. Right? It doesn't have to be like a straight line because you might have like a combination of charges. No matter what you are facing, there are some fixed properties, or I mean some sort of like a set of properties of electric field lines that you at least should be able to sort of like intuitively get. So take a look at this one, like part A. Okay, if you see the figure A over here, and somehow your electric field line is like in the form of a curve. It's not like a straight line, it's curved, which is possible. So that means every time that you are looking at one point, electric field always points in the tangential direction. Does that make sense? It has to be because, I mean, it's just like, wow, every time you draw a curve, right? But when you touch the curve at a point, and then you try to say, hey, there is something there, that there, it's usually you draw a curve just touching the vector that is pointing in that direction. So that's why if you want to go backwards, when you already have a curve, so it implies that at that point, you should have an electric field vector pointing in the tangential direction. So that's what it is. So that's the first property there. The direction of electric field is tangent to the field lines at every point. Okay, so if you're at point R, electric field will point tangential to it. At point P, tangential to it. At whatever point, it's all tangential to it. Okay, and the second thing, we have already discussed this. Look at figure B. So if I place like a cross section or like an area, okay, between point P and point R, so you guys agreed with me last time that at point P, the strength of the electric field should be stronger because the density of lines is higher. That's kind of makes sense, right? Because when you have like a very, very faint number of lines per unit area, it just means like, okay, the strength of the electric field is kind of low. So maybe the charge is far away, or maybe the amount of charge is kind of small, on and on. Okay, so the second one seems makes sense. Okay, the field is strong when the field lines is big per unit area. Okay, and it's weak when the density is kind of low. Okay, cool. Let's look at part C. Okay, the part C, this is already, you already agree with me as well. That's the convention that we already started with. Electric field start from positively charged particle and convert onto a negatively charged particle. Cool. All right, and this one give you a more complex setup, but it's still fine. Okay, look at this one. So the positive charge is bigger charge in comparison to the 2 microcoulomb on the right. So I mean, 3 is kind of like bigger than the 2, but 3 is positive, 2 is negative. So we kind of know that electric field is supposed to come out from the positive and converge into this negative. However, because the 3 microcoulomb on the left is a little bit bigger, so you can see the shape of the electric field lines, it's sort of like favored toward the bigger charge. Does that make sense? So it seems like the 3 microcoulomb is kind of like overwhelm a little bit of that negative 2 microcoulomb there. So that's the feeling you can get. All right, cool. All right, and part D, it's impossible for you to have 2 electric field lines intersecting each other. This is not possible. No, impossible, because it would be a problem if you're standing here and you have a crossing of the electric field lines. Then you're probably going to be confused, like, okay, which one, Dajan? Which electric field you want to go. You shouldn't have any crossing between electric field lines, because you guys know how to get the electric field is from the vector summation. So why don't you just complete your summation and get it done with, all right? So at one particular point, you can only have one value of electric field. That's it, because that's the vector summation at that point. So, right, you shouldn't have any decision to make at a point or anything. Yeah, sounds cool. All right, so those are some kind of like, I don't know, if you look carefully on this to these 4 figures over here, it's kind of like intuitive a little bit. I don't know. Maybe not. All right, but anyway, this is a business that make electric fields more complex than gravitational fields, because in the gravity, well, usually you have like a constant electric field, I'm sorry, constant gravitational field, right? It's like going down if you sort of like on the surface of the earth, or if you jump out of the earth and you look at the planets or whatever stars, and then you try to calculate gravitational field, it's still in the radial direction only. However, when you have charged particle, it's so easy for you to arrange like a very complex configuration of the charge distribution. So that's why the electric field lines would get complicated along with it. Yeah. All right, but don't worry about it. We're not going to draw this kind of thing. We just give you an intuitive idea of what are the properties of electric field lines. Okay. All right, cool. Keep going. All right, now, so once the comparison is kind of complete and the connection between the force and the field is just so easy. So there is one sort of like a setup that you can make an analogy between electric field and gravitational field, even closer. It looks more similar. Look at this setup, guys. You have an electric field that is pretty much uniform and is pointing upward, which makes sense, all right? Because down here you have like maybe like a plane of positive charge down here, positive, positive, positive here. And then in the upper plate, you might have like collections of electrons or negatively charged particle on the upper plate. All right, so between these 2 plates, eventually you have a chance to study more of this. But you can imagine that the fields between these 2 plates should have like a very straightforward direction. Is going out from a positive charge, go directly into the negatively charged. Then you should have like a uniform electric field here. All right, but if you're still confused about this one, now we'll talk more about this. All right, because this setup over here is actually a configuration for another electric device that we're going to study next week. All right, but for now, let's say, imagine that you have a uniform electric field. So this one just to mimic what you have with the gravitational field, that you have like only downward gravitational acceleration G. Same thing, we try to do that. And let's say somehow you shoot an electron into this area. Okay, so what would happen to it? What do you think? Of course, when you in here, so think about this. Let's say, let me pick a point over here. If electron is sitting there, let me call point P, so you guys know what I'm talking about here. So what is the force acting on this electron, guys? Electron is negatively charged. look at this, electric field is pointing up. Okay, so let me highlight that one. Electric field here is pointing up. Okay, it's fixed. But then we already said force is just charge times electric field, correct? So for this particular electron has the value of the charge to be negative E. You guys remember this, right? E is just 1.6 times 10 to the negative 19 coulombs, which is fine, just a constant of the universe over, right? All right, over here. And then you multiply by the electric field because electric field is pointing up. So the negative sign over here means the electron will experience the force pointing down. Cool? All right, we discussed this last time, and here, this is one big example here that you can see. There you go. All right, so that's it. So it means when you shoot an electron cut through the electric field line that actually has a uniform up direction, electron will experience a downward force. No matter where it is, if you move on to a next point, let me call point Q, doesn't matter, guys. The force still pointing down. And the magnitude stays the same, minus E times capital E, EE, yeah. See, no matter where you are. So does it look like familiar, this scenario over here? Yeah, this is exactly what happens in the gravitational field. When you just throw a ball horizontally and it's going to projectile down to the floor. Yeah, that's exactly what this is. Cool. All right, so this one just to emphasize how easy it is for you to calculate the force due to the electric fields. It's simply charge multiplied by the field. And the direction is definitely, you have only two choices. It's either pointing along the same direction as E, if that charge is positive, or it's going to point in the opposite direction if the charge is negative. That's it. Cool, simple enough. All right, guys. So if you have a chance, all right, once again, I would like you guys to refer to that website one more time. You still remember the allphysics.com there? All right, so I'm gonna once again share that. I have a shortcut for you guys here. So let me just give you that link there. All right, if you want to check that out, and I'm going to show you here as well. Oh, where is that? Okay, let me find that. Here we go. All right, guys. So if you look here, then this is the exact simulation that's sort of much better than what I just drew on screen. So over here, as you can see, this simulation is nice. You can pick the direction of the electric field. You can pick up or you can pick down. Cool. All right. And that particle is on the left there, that tiny blue balls over there on the left. And you can also change the charge particle from positive to the negative value by sliding this whole thing. Or you can even pick 0 actually. So if you pick the charge to be 0, so this is a neutral, there's nothing there. All right. And you can pick or you can select your initial velocity. All right. But now you can guess, if you just shoot in the particle with no charge, what will happen, guys? It will experience nothing. Yeah, we just go straight. It doesn't feel any electric field whatsoever. I mean, electric force, there's nothing. Okay. Now, if you decided to move up a bit, okay, in terms of the charge, then what you can expect here, guys, what do you think? Well, hey, Ajahn, so you pick a positive charge, but then electric field is going down, right? Pointing down. So when you, okay, let me reset this. Let me run it again. So what you can expect is it's going to curve down. See, it's a projectile motion here. Cool. All right. And now you can play with the mass if you like. You can increase the mass. And what you can expect is it's going to curve down again, but it's going to take a lot more time. Let's take a look at this. Yeah. So it's going to go further because now you have a heavier ball. So think of it that way. Okay. And then you can turn this upside down if you shoot in the negatively charged particle. So now it's going to go against the field. So instead of curve downward, it's going to curve upward. So let's give it a shot and see how it goes. There we go. Nice. Okay. So you guys can play around with this, and then I hope that will give you a better understanding and even better comparisons. between what is happening in the electric field and what is happening in the gravitational field. They're both having the same mechanics pretty much, okay, except the underlying force right here is from the electric field instead of gravitational field. That's all. Cool. All right. Okay. This is a very good one. I think this is way better than just simply take a look at the static figure in the textbook, I guess. All right. And there's a checkbox over here that you can say show voltage here, but we'll talk about that way later. Okay. But for now, I don't even see where those show voltage there, but okay, but that's later. All right. And actually you can adjust the distance between the plate on and on. And as you can see, when you adjust the plate, then the electric fields automatically change. Okay, so we'll have a chance to take a look at the relationship between the distance between plates and the electric field generated. Okay, all right. Actually, there is a times stamp on top as well, if you want. So you can, yeah, I think we can calculate everything pretty much. All right, guys, so that's kind of cool. All right, so I can stop sharing here and then let's go back to our slide. Okay, and I will get to your answer right now. So the question here is the direction of electric field will always be calculated assuming the test charge is positive, right? You can think of it that way, yeah, because we like the test charge to be positive so you don't have to flip your head every time. Yeah, you're right. So let's take the test charge to be positive all the time. I think that's the way to go. Usually we do everything positive first, right? And then for a general case, then you just slap in the -1 and then you just flip everything later. All right, but the direction of electric force does depend on the sign of the test charge. Okay, so think of it this way. I think the role of the test charge is done at the time of electric field calculation. So once you get that electric field calculated, the force just link to the field, okay, by calculating on the charge that you are interested in. And that charge don't need to be a test charge anymore. Does that make sense? Like this one. So we probably won't talk about this electron to be our test charge, right? This is a real charge that you want to put into an electric field. But the test charge that you were talking about probably will be used to do some calculation on what is the value of the field at this point, that point, here, there, on and on. So probably those can use the test charge there. But once you get that done, you already draw the conclusion that, okay, Ajahn, the electric field around this area from my test charge is E, and they are all uniformly distributed. And now you start doing the real experiments or whatever, do the real observation. And then just, okay, I'm going to shoot in an electron, bam, and see what happens. So there will be no more sort of like utilization of the test charge anymore. Does that make sense? So by something like this, so you don't have to think of the test charge too many times. Okay, just sort of like attach the existence of the test charge just at the time that you would like to figure out what the electric field at some point in space or something like that. Does that help? All right, guys. Very good. All right. Thanks for the question. All right, move on. So that's, once again, I use this exercise, sort of like this example to showcase the close relationship between the field and the force and how simple it is for you to go back and forth between them. Plus, if you really want to calculate this, I know you can do it, but I think you guys like don't like it that much because you have to go back and do like kinematic calculations. You have to use like, you know, one-dimension equation like acceleration, velocity, displacement, on and on, right? All right, so I might not be focusing so much on this because I think this is already something that you have already done so many times. So, all right, don't worry too much about this. All right, even though I might put this one in homework, maybe not. All right, but don't worry too much about this. All right, I think I am more interested in just the connection between the force and the field. So here we go. So it's time for our official announcement of the Coulomb's law introduction over here. It's right now. So this is where things started in the textbook, right? They will introduce to you Coulomb's law first. So the Coulomb's law, we're just talking about what is the force between two charges. So you have a pair of charges here, Q1, Q2. Let's say it's sitting here. That's Q1, and that might be another one here. You call it Q2. Okay, and then Coulomb's law is explaining what is the force between these two charged particles. Now, I'm going to talk about this one just one last time, guys. One last time. We can think about this in terms of the field. Okay, let's start with that. So Q1 will generate the field everywhere around it. Okay, and at the location of the Q2, let's say that the separation between them is R. So at the position of Q2, the Q1 will generate the electric field pointing in outward direction. Make sense, guys? Okay, how much? You say it's just K Q1 over R squared. Cool? And you can put R hat into it, just make it a vector quantity. All right, what is the force on Q2, guys? Well, John, that's easy. The force on Q2 is just going to be Q2 times that E. Done. And this is supposed to be the time of the sound effects here. And what is that? So that F, so let me call this F21. So that's a force on the particle number 2 due to the charge number 1. So I can say F21 is just Q2 times E, the red one, right? So let me do the color coded here, times E that we just calculated. And it's just, see, K Q1 over R squared and Q2. So it's going to be K Q1 Q2 over R squared. And you are done. Okay. All right, and you do the same thing equally on the opposite direction. So think of Q1 being affected by Q2. So the Q2 itself will generate electric field around it as well. So they have their own electric field. Cool. All right. At the position of Q1, electric field due to the Q2 will point outward as well. So let me sort of like put it backward here. See? So let me call this E, the green one. Okay. So this is the green electric field. How much is this? It's just be K, the charge generating the field Q2 over R squared. All right. But of course, at the position of Q1, what will be the force that Q1 experiencing? Well, that's easy. So force on Q1 due to the particle 2, so let me put F12 there, is going to be just the Q1 itself and multiply by the green electric field there. Cool, easy. And then what I get is going to be K Q1 Q2 over R squared as well. And you are done, see? So this formula is symmetric on both sides. Q1 will experience the force due to the Q2. Q2 will experience a force due to the Q1, but we explain everything in terms of electric field. And then you link the field to the force by just multiplying the charge at the location of the field, and you are done. You get back, what is this? This is Coulomb's law. Voila, all right, and it's following Newton's third law, action equal to reaction. Q1 is kicking the Q2, Q2 also kicking Q1 back. That's it. Okay, and what is the K? Now it's officially announced here. It's right there. Here we go. All right, so K is 9 times 10 to the 9 Newton meter square, but Coulomb square. Oh, I think I put the wrong number there, guys. Sorry. Maybe last lecture I put 9 times 10 to the negative 9. Sorry, it has to be 9 times 10 to the 9. All right, no, there's no negative 9. I was just thinking of nano thing. So in my, sorry. All right, guys, just to emphasize again. All right, so this is 9 times 10 to the 9. Okay, not negative. There's no negative sign there. All right. And in the future, which is about maybe next week or the week after, we can re-express the K in terms of another fundamental constant of the universe, but that's wait for later. For now, the only thing that you need to know is there is another way that you can describe the K. which is the Coulomb constant here, in the form of 1/4 pi epsilon naught here. All right, 4 is constant, pi is constant. The epsilon naught, that's another constant there. All right, well, we have a chance to get back to this, but don't be sort of like confused if sometimes you see the formula is using the K, or sometimes the formula is using 1/4 pi epsilon naught. They are the same thing. Okay. All right, guys. And that's pretty much, see, it's done. So it seems like, I don't know, it's feel natural to me for you to understand electric field first. And then we just give you a connection between the field and the force, and you're done. So you can understand everything in one step, right? Without going through these formulas twice. Okay, any questions so far? Kind of cool. Okay, all right, if that is the case, then this is explaining what I already just did in the previous slide. The force between these two charges are exactly the same amount, but they are pointing in the opposite direction and acting on the different objects, of course, but it's going to follow Newton's law. It's the Newton's third law, so you cannot avoid that, all right? That's what it is, okay? And still, if you have more than one forcing acting on one particle, what you need to find out for the net force on a particle, you just do the vector sum of all those forces. So that's nothing new. We have already done that. So now you have choices to make. You either want to do the calculation of the force and then you do the summation if you want, or you can do the electric field first by taking the E from E12, E13, you take, well, electric field doesn't have any pair. So it's supposed to go like electric field net is going to go like E2, okay, like E2 plus E3 plus E4, on and on. And at the end, you multiply the Q1 just to see what is going to be the net force acting on charge number 1, for example. Okay, cool. So they're going to give you the same final answer. It just depends on which approach you prefer. You want to get the field and then down to the force at the end, or you're just going to take each pair and do the force calculation and then you do the summation at the end. Same thing. All right, let's take a look at the example and then it will be clearer what I'm saying over here. All right, take a look at this. In the figure, 3 charged particles lie on an x-axis. Particle 1 and 2 are fixed in place. Particle 3 is free to move, but the net electrostatic force on it from particle 1 and 2 happens to be 0. So once again, you have like a perfect cancellation of the electric force or electric field at point charge number 3. If the distance L23 and L12 are exactly the same, they want to figure out the ratio between Q1 and Q2. Cool. So this is a good example. You can approach this problem in 2 ways, just like we already discussed. You can start from the field. Okay, let's do that first. And then I will just pop up the force right away after you got the fields down. So let's try that. All right. So let's start by doing the field calculation first. Okay, so once again, so I think everyone should be comfortable sort of drawing the vector due to the charge that generating the field now. So let's start from charge number 1. So what should happen at point 3 due to the charge number 1? Because the charge number 1, you don't know the type of charge. So let me call it Q1. So I don't know, is it going to be positive or negative? So let's think of it like, let's say if it's positive for now. If it's positive, that means the electric field at point 3 due to Q1 is supposed to point outward. Does that make sense? All right, so let me name this E1 vector. Do you know the magnitude? Yeah, but no problem. The magnitude of E1 is just going to be K, the Q1, the charge generating the field, divided by the distance from Q1 to point 3. And because they said the distance L23 and L12 are exactly the same, so let me name this one just L then. So it's just easier to write. So it's going to be 2L squared. Cool, that's done. I know the magnitude of the E1 electric field. Let's do Q2. Let me put the green color there. All right, but you guys know Adan, to have a cancellation, the electric field from Q2 is supposed to point in the opposite direction to the E1. Does that make sense? So at least you know if you already treat Q1 to be a positive charge, then Q2 is supposed to be a negative charge. All right. Or you can do it the other way around, doesn't matter, but at least you know that these two charges, Q1 and Q2 must have opposite charge. That's all you care about. Okay, so with that, the electric field at point 3 is going to point towards Q2. That's what we want. And we want perfect cancellation between the two as well. All right. Now, what is the magnitude of E2, guys? Just like that K, charge generating the field. See, I don't have to take the negative sign into the calculation anymore. We just care about the magnitude. Divided by the distance. Now the distance is only just going to be 1L. So you just say L squared. And because you just said the field is supposed to be 0 because you want the force to be 0. Does that make sense? So all I need for the condition of the final calculation is just setting Q1 and Q2 to be the same. I'm sorry, E1 and E2 to be the same. All right. And at this point, now it's sort of clear. If I place another charge here, let me put like a big Q here. If at the location number 3, I have one big charge, it doesn't have to be big, just one charge. If I have a charge Q right there, capital Q, if I look at the force instead, doesn't matter. That capital Q there will experience the force due to E1 to be Q times E1. With me, guys? And the force due to the E2 will be Q times E2. So it's just like you have an equation of E1 equal to E2, and then you multiply through by the capital Q. So what you end up with is just going to be the F1, okay, you can say F31 equal to F32. See? The force on the particle number 3 due to the charge number 1, that's F31 there, equal to the force on the particle number 3 due to the charge number 2, F32 there. See? So I'm saying these two approaches are going to be exactly the same. You can talk about the field or you can talk about the force, right? It's just a matter of just extra charge being multiplying to the field. You get the force. All right, guys, keep going. So E1, you already figured out, is KQ1 over 4L squared. And that's going to be equal to the green KQ2 over L squared. See? And eventually Q cancel anyway. You don't even have to care. So this is the reason why, to me, I don't know, I prefer electric fields, because every time that we talk about force, you always talk about a pair of charges. And that's, you know, you always have to, you know, hey, where is the other charge? Where is the other charge all the time? But if you talk about the field, it's like a single charge generating the field. So you're just looking at each charge one at a time and just keep going and calculate the field on, and you're done. And at the end, if you want the force, just slap in the charge there, multiply by the field at that location, you're done with the force. Cool? All right, so with this, K also cancel, L also cancel, and now you end up with the final ratio. Q1 over Q2 is going to be 4, and you are done. All right, it's supposed to be like a big applause here. All right, cool, guys. And that makes sense because Q1 is further away from point P than Q2. So you have to compensate by having a charge to be bigger, right? For you to be able to get the cancellation of the field at point number 3. Yeah, something like that. That makes sense. Okay, guys. So I think this is very good, and I hope it's sort of like give you a, you know, some, I don't know, some confirmation that field and force are the same business. Okay. All right, guys. So I think this is a good point to take a break, and we'll come back with more exercises. Yeah, sounds like fun. So we have like a couple more that just to confirm that you guys know what is going on here. Okay. All right. There's a question here. It would be the same if Q1 is negative. Yes, exactly right. So you can switch the role here. You can take this to be negative and take this to be positive, because what they care about is just the ratio of the charge magnitude. So they didn't really, I mean, it could be both. It could be as long as the charges are opposite, you are good to go. All right. They just only care about the magnitude of these two charges. Cool. All right, guys. So let's take 10 minutes break here and then we'll come back with more exercises. Yeah, sounds like fun here. Okay, so let's try a couple more examples, shall we? All right, I think things will get sound like more natural to you guys when you have seen a couple more exercises and then you know how to sort of like choose or pick which approach you prefer. Yeah, you want to go with the electric field or you want to go with the forces, up to you. Okay, so let's start with this. You have 3-point charges are arranged as shown in the figure. Find the vector force on the 5 nanocoulomb charge. Okay, here we go. So with this, so I'm going to show you, let's see if I want to go through the route of doing the force calculation, all right, and see how it goes. All right, just change the mood a little bit here. So if you would like to go with the force, every time you calculate using the Coulomb's law, you need a pair of charges at all times. Does that make sense? All right, because it has to be the force between a pair of charges, yeah? So because now they're focusing on what is happening to the 5 nanocoulomb charge, which is, okay, let me highlight red over here. So it's sitting at the origin at this point. So as you can see, you have 2 pairs of charges here. So it's between the red and the blue and the red and the orange. Does that make sense? Okay, so but of course, your attention is going to be on that 5 nanocoulomb charge, the red one. You don't have to worry about force acting on the blue or the orange one there. So don't worry about it. So let's focus on the red. You can see that now there will be a force acting between this 5 nanocoulomb and the negative 3 nanocoulomb. And you guys know that the opposite charge attract. So that means the force that is acting on the 5 nanocoulomb charge will be pointing downward. Does that make sense? Okay, maybe I draw a small vector. It's going to be a little bit easier to see. Here we go. So you get a downward force. The blue pulling down the red. Cool. All right, how much? So what you can calculate is the force on, let me call this charge number 1 here. And let me name the blue to be number 2 and the orange to be number 3. So charge on 1 due to 2, let me put it as F12. Magnitude is going to be the K times the Q1 and Q2, right? The pair of charges. So it's going to be, let me write the numbers down so you know which one I'm talking about. 5 nanocoulomb and the 3 nanocoulomb. Does that make sense? So it's a K, Q1, Q2. Okay. And then divided by the separation here, which is given to be 0.1 meter. And then you take square of this one. That's it. That is the amount of force acting on that charge number 1 due to the charge number 2, the blue. Okay, now move on to the pair between the red and the orange charges. They're both positive. So that means you're going to get a repulsive force acting on the charge number 1, the red one here. So what you get is going to be a repulsive force. So let me put it here. It's going to kick this one to your left. Make sense? All right. And let me color code it here. Let me use the orange color as well. So I'm going to name this F13. There you go. F13 vector is right here. Okay. This down here is an F12 vector. Cool. All right. And now the magnitude of the F13 is going to be the K, the Q1, Q3. The pair is always comes in pair. So it's going to be 5 nanocoulomb, that's the Q1, and going to be the 6 nanocoulomb, that's for the orange one, and then divided by the separation, which is 0.3 meter, the whole thing square. Cool. All right, now you have the magnitude and directions of these two forces. You can now find out what is going to be your net force. Your net force is going to be the Pythagorean theorem, right? Just add these two together, you get this one down here. All right, let me call this the sigma F, the total force vector over there. So if you want to find out what is going to be the total magnitude, right, the value of the force, the sigma F is just going to be the square root of, and now you just take the F12 square plus the F13 square, everything under square root, and you are done. You get the magnitude and you get the directions. If you want, I mean, you can take the ratio, find out what should be the theta, everything is fine. However, there is an easier way for you to do it, to write the vector force. Okay, so follow me here. I can also do it like this. If you already found out the magnitude, you might have to figure out the direction, right? Just put the arrow here, just say, right, it's pointing like, you know, toward the downward left, whatever. But if you want to use the ij notation, that will save you a little bit of time. So what I can say is just like, okay, Ajahn, that F13 there is pointing in the negative x direction. So what you can do, you can just say it's an F13 magnitude, and then you just follow with the negative I hat. You guys with me? So you just say, hey, you have the negative x component of the force equal to the magnitude of F13. And then you just say, okay, plus, now you can see F12 is pointing down. So you can just say you get F12, and then you have a negative j, there you go, it's pointing down. And this is perfect. This is already a vector format for the force vector. You are done. Cool? Already. All right. And now you can repeat this whole process by doing the electric field calculation first, if you like. Okay, so I think this is maybe a good practice for you to try, but now you should be able to sort of like see what should happen without redoing the whole thing too much. If you look at just the field at point, the location of the charge number 1 first. So that means at first, you don't need to put charge number 1 there, right? Because you want to figure out the electric field first. So it's the same thing as you just like Ajahn, you just have to forget about this 5 nanocoulomb charge. You just don't have to put it there. Does that make sense? If you just want to take the field, it's going to be just the field from the charge number 2, the blue, and the field from the charge orange number 3, yeah? And you just figure out the net electric field. And then you just pop the 5 nanocoulomb charge, the red charge, toward the end. Just multiply by the 5 nanocoulomb charge at the end. You get the same result anyway. Cool? Is that clear enough? I hope. Already. Okay, so just to be able to write out what I'm saying over here, look at this one. Here we go. So I'm gonna just take from this line here, sigma f equal to square root, okay, F12 is just Q1 E2. You guys with me? Yeah, if E2, just saying that what it means by electric field due to the charge number 2, plus F13 is going to be Q1 times E3. Does that make sense? E3 is the electric field due to the charge number 3. You multiply by the Q1 in both terms. That means I can pull this one out, that Q1, and you are left with just E2 square plus E3 square. See? So that's complete the whole thing that I'm saying, that if you would like to take the electric field calculation first, then it's just like find out what should be the net electric field. And then your Q1 just come back later at the end. Get the same answer anyway. Cool. All right. So for those of you that still confused a little bit, I would just recommend that you try both methods if you want. But for those of you that sort of like, okay, I got it, John, it's just they are the same thing, then you can just sort of like, you know, run your whole protocol in your head and all this stuff. Don't really have to do it on paper. Cool. All right, try one more, shall we? All right, things will get more complicated. That's possible. Let's try the next one. So in the figure, the particles have charges Q1 and negative Q2. So it means Q1 and Q2 are positive in charge. Q3 and Q4 also positive, opposites in charge. And distance A is given to be 5 centimeters. What are the X and Y components of the net electrostatic? Okay, you have seen this word twice already. Electrostatic here, and I think you have the electrostatic somewhere there. There you go. So don't worry about it. The reason that they have to put this adjective over here, because what you're doing over here is electricity, but as you can see, everything is pretty much fixed in place. You don't have any movement, you don't have any motion, you don't have any acceleration, you don't have any velocity. So you are looking at electrostatic. It's just not moving, right? So it's a fixed positions of charges. So that's why all the effects over here, you assume that the force that you experience, the force that's sort of acting on this, the action, reaction, everything, even though it's already there, but you assume that everything is still static. You don't, even though the charge will get kicked out, but I mean, you don't care about what is happening next. So you still don't worry about dynamics of the charges movement. Okay, cool. All right, so that's why we have the adjective saying electrostatic, because we assume everything is in positions, no movements yet. Because you will see later when things move, you get everything else that is the second half of this theory, which is which is magnetic. All right, but I don't know how far can we go. We might not be able to get to magnetic, but at least that's what it is at this point. Everything is static. Okay, now find the electric field, electric force on particle number 3 due to the other 3 charges. Okay, and write everything down in terms of the vector notation, x, y components, on and on. Okay, so just to contrast this exercise with the previous one, I'm going to perform this calculation using the concepts of the field first. All right, and then I'm going to take in the charge number 3 at the end. Sounds good? All right, so you can see the difference between the two. So if I am looking at that, then what I'm going to do here is I'm going to just take away my charge number 3. Forget about it. Okay, you don't need to worry about this charge at the moment. Cool. All right, all you have to worry about is just what is going to be your net electric field at this point. Yeah, just find the net field at point number 3. So let's start from charge number 1, shall we? So the charge number 1 up here, okay, let me put 100 nanocoulomb there, and let me use that color red there. So the good thing about this one is it's positive. So the electric field will pointing away from it. So let's start with the red one. Here we go. So the electric field due to the charge number 1 will pointing down at the location of the charge number 3. Everyone still with me? So far so good. All right, cool. Keep going. What about the charge number 2? So now let me use the green color here. So the charge number 2 over here is the negative 100 nanocoulomb. So that means the electric field will point towards it at the location of charge number 3. So if I just draw, sort of like give you a line of sight here. So that's what, yeah, that's a radial direction having the charge number 2 at its center. So what you have over here is you're going to get the electric field due to the charge number 2 at the location number 3 point towards it. Does that make sense? Okay, negatively charged particle generate field point towards it. Now move on to the charge number 4. Charge number 4 is also negative right there. All right, so let me mark on this one. Let me use the blue color here. It's negative 200 nanocoulomb. I'm just going to draw a line of sight for you guys. So over here, oh, I'm sorry, wrong direction there. There you go. There, okay. That's the line of sight there. Okay. So now because the charge number 4 is negative, so that means at the location number 3, you will have electric field point towards it. Cool. So that's it, guys. So these are the 3 electric field vectors that you need to sum them up. And once you complete the summation process, that's it. That will be your net electric field at the point of the number 3, at the point 3 location there. All right, so let's start with the red. Let me name that one E1 then. E1, okay. So we can figure out the magnitude of the E1 easily by saying that it's going to be K, the Q1 over, of course, the distance is going to be A squared. Already. All right, you can plug in the number here if you want, but I still recommend that you don't do the full calculation just yet, but just sort of like substitute it in if you prefer. I would love to have K with me, just K. Q1 is the 100 nano Coulomb. Nano is 10 to the negative 9. A square, I still like to be A square. All right, so almost like haven't done any substitution at all. Okay, now E2. Let me name this one E2. There you go. All right, so the E2 magnitude is going to be K. Q2, of course, the charge generating field, divided by the distance. Now the distance is going to be this hypotenuse here. So because you have the isosceles, sort of like a triangle over there, so this one is going to be A root 2. All right, so that's good. So it's going to be A root 2 the whole thing squared. All right, substitute a little bit. Just keep the K. The Q2 magnitude of the charge is still 100. I don't have to take the negative sign here. Nano is 10 to the negative 9 divided by A root 2 squared. So I have 2A squared. Pretty good. Keep going. I can figure out the blue vector. Let me name this one E3, electric field number 3. And the magnitude is going to be K, Q3 over, now the separation is only A. It's A squared. So it's going to be K. The charge number 4 is 200 nano, 10 to the negative 9. Actually, I don't even need to times the 10 to the negative 9, but just for clarity here, over A squared. See, so you will be able to figure out all of these electric fields, E1, E2, and E3 without a problem. So what you have left to do is just combine them all. How do you do that? Up to you, but I think maybe the easiest one is just doing the components of the vector, right? Because you can see that E1 is already along the y-axis. E3, the blue, is already along the x-axis. So there's only weird one out. There's the odd one here is just the E2 is sort of like at some angle, which is the angle I think is 45 degrees. So it's no big deal. So what you can do is you can split your E2 into two components, the one along the x, the one along the y. So let me use the black color here. So I can split this one, take the E2 along the x, and then split another one here, E2 along the y. Cool. All right. And of course, both of them will be E2 cosine theta, 45. So I can call this E2 with root 2 over 2 if you want. You with me? All right, because sine or cosine 45 is just root 2 over 2. So you have E2 root 2 over 2 in the vertical direction as well. And that's it, guys. So you can figure out, so what I can do is this, the net electric field along the x-axis. Let's do one component at a time. You have the blue pointing to your right, the black, horizontal black pointing to your right. So the net is just the sum of the two, just pointing in the same direction. So your net x components of the electric field is going to be E3 plus E2 root 2 over 2. You're done. That's it. All right, you can plug in a number, whatever you like later. Sigma EY, the net electric field along the y-axis. Now you can see that the E2 components that's pointing up, that's good. Let's say up is your positive. That's the common direction that you already picked. So you have the positive E2 pointing up, E2 root 2 over 2. That's the up component of the E2. And then E1 is actually pointing down. So you have to subtract that E1 out. Okay. And if you want to put them into a vector format at the end, you can combine this and write it as a sigma E total, sort of like a sum of the electric field, is going to be just sigma EX I plus sigma EY J hat. You are done on the electric field calculation. So you're not bad. So this is pretty straightforward. And now to get to the force, see, I already completed the field calculation without caring what is going on at the location of number 3, right? But now at point number 3, you have a charge waiting for you. I'll bring back that charge number 3. So let me use the black color there. There is a charge number 3 waiting there. Okay, so what is the force on it? Oh, let me put like a big arrow over here. The force on the charge number 3, it's just going to be Q3 itself, the charge at that location, and then multiply by the sigma E vector that you have already figured out. There you go. And you are done. That's how easy it is. Okay, so that's why it's your choice. You can do force calculation. So if you do the force, you have to pick each pair and do the calculation of the Coulomb's law, each pair at a time. You start from 1, 3, followed by 2, 3, followed by 4, 3, and then at the end, you just sum all those force vectors together. Or you can do what I just did. Take away that Q3 first, just get out of the picture and everything. Calculate the electric field at point number 3. From charge number 1, you have E1, charge number 2, you have E2, charge number 4, you have E4, and then you sum all those electric field first. And at the end, to get back to the force, you just bring back that Q3 charge and multiply by the net electric field at that point, and you are done as well. Not bad. All right, so I hope, after these 2 lectures, I think you already got what it means by, yeah, I'm keep saying that field and force are pretty much the same thing. That's what I'm saying. All right, and plus, you get to see the full form of the Coulomb's law that can be interpreted in terms of the force between 2 charges, or you can interpret in terms of like the field generating by a charge. And then there is a second charge exists at the location of the field generated by the other one. 2 are the same. Cool. Already, very nice. Now, maybe this is a moment that you have been waiting for. All right, just to make things sort of like, nice and clean and compact today, because I'm afraid that the voice is not as great as before, and because this is like sort of like the location is kind of unusual here. So I'm going to give you one exercise that we're going to incorporate calculus into our calculation. All right, the reason I say I just only introduce one, because I think this will have to take time. All right, and you have to sort of like have this part of your materials, absorbed into your brain a little bit. It might take a week or something. All right, so I'm going to show you if the charge that you are dealing with comes in a uniformly distributed charge and it's continuously distributed. When you say continuous, it's just like this. So you're not getting like a piece of Q anymore, like 1Q1 here, 1Q2, 1Q3, and then it just calculates electric field or electric force from each individual charge. Okay, so those charges, you can call them point charge. It's come in a point, right? Discrete. But instead, you have like a big continuous charge, which kind of makes sense, because if you imagine like you have like a bunch of charged particle, like when I say a bunch, you have to think of like Avogadro number. It's like 10 to the, I don't know, 23rd molecules or atoms or whatever. And then those charges running around like crazy. And then you don't have time to think of it in terms of individual charge anymore. So that's why the model of having a continuous charge particle is important, because that's pretty realistic, right, in the actual scenario here. So how can we extend our Coulomb's law or charge or field calculation that we did with the point charge and move on to a continuous charge distribution? The idea is simple. Calculus comes into play right away. You have to DIY, do it yourself. You have to slice or cut that continuous charge distribution into pieces. Like you have to cut into many pieces, and each piece will be treated as a point charge. Does that make sense? Because you already learned how to deal with a point charge. Now you have like a bunch of charge coming continuously. All you have to do is just slice them out and treat each slice as a point charge. And once you're done with that, you just keep going to the next, keep going to the next, keep going to the next, and then you add them all into a final electric field. But you have to add them continuously anyway. So that's where the calculus comes in. Okay, cool. All right, so what I'm going to do is this. So if you have a bunch of charge coming like this, you slice charge into a tiny piece, and that tiny piece will contain a tiny charge. I can call this dq, even though you can call it delta q first, and then you shrink it down when everything go infinitesimally small. Remember this word from calculus? When things approaching zero, then that delta turns into a differential, something super, super small, right? So this one going to zero there, all right? And then you say, okay, that amount of charge will definitely generate the field at the point that you would like to calculate the field. And that still follow Coulomb's law. So that means at location P, the electric field will still follow the same equation, K. The charge generating the field, dq. The separation from that charge to the point of calculation, you can call it R, and then you put the square into it. See, haven't done anything new. The only thing new is the charge is just super duper small. That's all. It's do right here. It's super small. So that's why you have to worry about it. But for now, because your charge is small, your field probably super small as well. So I'm going to put the differential term there, the notation there in the front as well. There, see? So they comes hand in hand. The dq, super small charge, will give you dE, the super small e. And then the next step is you just have to move on, do the next one, slide the next one, slide the next one, slide the next one, 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 the next one. Each one will contain dq, 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 dq. And each single dq of yours will generate a different dE, 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 dE. You guys with me? Over there. Here we go. dE there. dE there. There's going to be like crazy bunch of dE on and on and on. Crazy. Crazy. Okay? And at the end, you want these all dEs to combine into a final electric field. So in your heart, you just want to do the summation. Yeah. If that dq is not that small, you can call it delta. But when things go to zero, that summation turns into, you can guess it. Yes, the integral. And that's it, guys. It's supposed to have like sound effects at this point. All right. Saying things here is easy. Okay. I can just say, okay, you just slice the charge into a tiny piece, and then you do the calculation of that tiny piece. You get the tiny electric field, and then you do the integral. I mean, conceptually, it's fine. The reality is harder, right? So to be able to understand this one more clearly, I think take a look at example, and you'll see how it goes. Okay, guys, this is the minimum requirements. And this is supposed to be like a college physics problem here. All right, this is, I mean, once in a lifetime thing. You have to do this. So now you have a rod of length L, and somehow on this rod you have a uniform positive charge distributed around this rod uniformly. So that means no matter where you look at it, the charge density is going to be the same. Okay, I will just keep this word at this point, just say density. Okay, now let's say the total charge over here is Q. Oh, sorry, there's a highlight. Okay, let's say the total charge on here is Q. Okay, calculate the electric field at point P on the left, located along the long axis of the rod and distance A from one end. So it's already set up everything. And once again, everything that you have to do in calculus, you're supposed to have a sort of like coordinates going on as well. So what I'm going to do is we're going to put point of interest that we would like to calculate the electric field to be at the origin as indicated there. So once point P is already at the origin, the left ends of the rod will be at the distance x equal to A. Does that make sense right here? Cool. What I'm doing here. All right, so here, that's x equal to A. All right. And of course, the right end of this rod will show up at A plus L. No problem. Okay, so far so good. All right, now, so let's start the process, shall we? slice this piece first into a tiny piece. Chop, chop. Let me do the chop, chop thing. Okay, that is my tiny slice. And that tiny slice will include a tiny amount of charge dq there. Okay, now you can forget everything else. Just treat this dq, like pay attention to this dq. How much electric fields you will get from this dq. Let me write it, Ajahn. We assume everything to be positive at this point. So you're going to generate electric field pointing outward like this. Let me call this tiny e. You guys with me now? So you see what I'm saying here? So think about this. This is what happens. When you slice your charge into a dq piece, that dq piece still generating an electric field at point P. You call that electric field generated dE. How big is the dE? Follow Coulomb's law, K dq over now the distance. What should be the distance here? But John, this is already on the x-axis. That's kind of nice. When it's already on the x-axis, the location of this, the x value of this is already give you the distance here. So that's why that's a benefit of putting point P on the axis plus located at the origin. So it's an x squared, can be used right away. And the good thing about this one is x is a variable which can be used for other location of your dq. Does that make sense? Think of this. If I do another slice, chop, chop right there, that dq slice will generate another de here. And I'll do another chop, chop over there. I mean, it's supposed to continuously happen. And then another slide, flap, flap, another dq, it will generate another de there. Another slide, chop, chop, you have another de there. Another chop, chop, another de there. Another chop, chop, another de there. And chop, chop. And then you keep doing this slice. You keep doing this de calculation. But as you can notice, no matter where your slice is, your electric field generated at point P can be used, it's going to follow this exact relationship here. Isn't that nice? So that means this equation over here allow you to be able to calculate electric field from any location on this rod, which is very nice. Okay, so you're just going to keep doing the chop chop thing, slice, chop, 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 chop. No matter where you are on this rod, this equation works. So the only thing that you need to do at the end is just look at the left. Every slice that you slice this will generate DE, 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 crazily many DE on your left. See that? So what you have at the end, you have to just calculate the net electric field at point P is going to be the summation. But this summation is happening on things that continuously and approaching infinite sum because your dq is super, super small. So this summation turns into integral of dE. Does that make sense? And that dE is already given as a q k dq over x squared. So what you do the calculation from the left end of the rod. It starts when x equal to a. That's the left end. And then you do the summation by varies the x value until you reach x equal to a plus l. Wow, that's not bad. Almost done, except, Ajahn, you are integrating under the dq variable, the q variable, but your integrating variable is x. That doesn't make sense, okay? Because what you have to, every time you do the integral, of course, the function of that you want to integrate must match your integrating variable, right? So that's maybe the last stop that you need. If you can convert one to the other, then your job is done. How to do that? That's not bad. It's actually easier than you think. Here we go. Look at this. Every time that you slice a piece of charge, chop, chop, over here, you said it's contained tiny charge dq, right? But every time you slice, fap, fap, then you also take up some space dq as well. Yeah, it takes the space dx as well. So There must be some relationship between X and Q here. It must be here somewhere. dq is already, it's contained inside the dx interval here. So what kind of linkage that dq can get to the dx? And that's where the density word that I told you about just gonna come back here. When I say density, what does it mean? Think of it this way, guys. If the whole length of this rod L contain the charge Q, but if I only take just the x of it, do you think how much charge will I get? What do you think? How much charge should I get? dq. I know it's dq for sure, but what kind of dq will link back to the dx? Through the known value of capital Q and that length L. What do you think? So what I'm saying over here is this: the ratio must be fixed. When I said ratio is fixed, because we said the charge is uniformly distributed, correct? So I know the whole rod will have the charge per unit length of Q over L. This is fine. But if you zoom in and just look at this, John, if I only care about the slice of yours that contain dq here, it takes the only space of dx. The ratio of dq and dx must still be exact same ratio as the capital Q and the L. What else can it be? Does that make sense? Make sense? The ratio stay fixed. It cannot be changed. Yeah, so that's why this is the one that I'm talking about. We're going to call this the density. Isn't that cool? But of course, it's not the density that you're familiar with, because most of the time when you talk about density, you talk about per unit volume, right? The reason is you use the volume because it's three-dimensional stuff. You have the width, the length, the height. But here, it's a one-dimensional charge. The charge is being arranged only along the x-axis. So you don't have any width. I mean, you don't have any depth. You don't have any height. You only have the length or the width or whatever. So that's why you call this charge density anyway. But it's 1D, one-dimensional charge density. And sometimes they refer to as that lambda over here. It's the charge per unit length. All right, and you can name it, it's a charge density. Cool. All right, so with that, that means, well, Ajahn, nice. So if you have this ratio fixed, so it means I can write dq to be q over L dx, or if you want it shorthand, you can say it's a lambda dx. Okay, why not? So that's how you convert dq into something of dx. Okay, and that allow you to move on to the next step. Now I can pull k out from the integral. That's easy to do. The lambda dx will be in the position of the dq. Now you have an x squared down here. Now everything is under x, so I don't have to put x equal to something anymore. It's from a to a plus l. And because in this problem over here, lambda is a constant, I can pull lambda out as well. And now the only integral that you need to evaluate is the integral of 1 over x squared. And everyone knows how to do this. It's just 1 over x with a minus sign. Cool. And then you integrate from a to a plus l. You guys with me here? See? And then now the last step, you just plug in the upper limit, subtract out the lower limit. And because you have a negative sign in it, so you can do is just 1 over a minus 1 over a plus l. And at the end, you can put, do some, manipulation and just like smooth things out a little bit. You can say k, capital Q over L, that's for the lambda. And then you can just do the common denominator, do some numbers here. It's going to be L over a plus L if you like. Cool. And that L will cancel. And that's it, guys. It's done. That is the electric field at point P. I'm supposed to have like a big applause here. So not bad, you think? It's doable. maybe not, but I think this is a good starting point. How can we incorporate calculus into our calculation here? And as I said, once in a lifetime, or you can think of it, this is, you deserve to do this because this is a college physics class or something. That this is supposed to be in our content or whatever. We have to do this, cannot avoid this. All right, guys. So I think this is a good place to stop. So you have like one big exercise for you to review. And if you eager to, move on, you can look at the next problem. This is going to be tougher, of course, definitely. And then we're going to have one more of that to do when it's curved. All right. But I'm not going to go beyond this anymore. So don't worry about it. I'm not going to do anything too complicated. I'm not going to eventually impose something that will lead you to like a super difficult integral, right? It's going to be something that is very doable by hand, and the configuration is simple enough for you to pretty much like set up the whole thing and then finish the whole mathematical procedure. Okay, so that would be, I'm pretty sure it's not going to be that difficult. All right, but you have to get yourself used to this kind of calculation first before you can, do something more complicated. Sounds like a good plan? Okay, all right, guys. So I think this is it for today. And next time we'll attack more calculus. It's like not physics anymore. All right, guys. So have a good weekend. I will see you guys next Thursday. Yeah. Okay. And then soon I will post the poll so you can vote when would you like to have your second exam. Yeah. All right, guys. So take care and I'll see you next week. Bye-bye.